Hi everybody, welcome back to another video. In today's video, we're going to be doing a few problems related to indefinite integrals, just like I said I'll be covering in my previous video. So I've got an interesting set of sums which we can solve together. So without any further ado, let's get into it. So our starter problem is the integral of x cubed minus 1 divided by x cubed minus x dx. So as you can see, the trick to solve this integral is to keep adding things, expanding it, and using identities. So this is an easy integral, let's get into it. So we have x cubed minus 1, and this is just the a cube minus b cube identity. So what we can do here is we can just rewrite this as the integral of x minus 1 into x squared plus x plus 1, right? We're not changing anything. Divided by, now here we have two x's, so we can factorize x out, x into x squared minus 1 dx. Now as you can see, there's another identity here, x cubed minus x squared minus 1. So what we can do is we can just rewrite this as the integral of x minus 1 into x squared plus x plus 1 divided by, now we have x into, now what we can do is we can kind of expand this into x plus 1, x minus 1, because this is none other than an identity, right? So we can cancel off this with this, so we are just left with the integral of x cube plus x plus 1 divided by, now here at this rate we can multiply this with this, so we can open the bracket x squared plus x dx. Now aren't you seeing something common between the numerator and denominator? You have x squared plus x and x squared plus x in the denominator as well. So we can kind of, the beauty about integration is you can always split it into two parts, partial integration. So what we can do is we can take the integral of this side, x squared plus x divided by x squared plus x, plus you have the integral of 1 upon x squared plus x. We're not changing anything. Dx over here, keep forgetting to add the dx here. Okay, so here at this rate, we just keep cancelling this and this, right? That's very easy. So we're just left with the integral of 1 dx, which is just x ultimately. So it's just dx plus you have, now here you have 1 divided by x squared plus x. So, okay, we'll just rewrite it. So the integral of, we have 1 divided by, now x is common, so we can kind of remove that as well. X into x plus 1. Okay, so I kind of got the trick. So what you want to do is you basically want to, add more things. You want to add something in the numerator and minus something, right? So what we'll do is we'll add an x in the numerator because we can cancel off that with x plus 1. But if you are adding something, we also have to minus something. So now the integral of dx will just be x plus we have the integral of 1 divided by x. So what we can do is we can say x minus 1 plus x divided by, now here we have x into x plus 1 dx. Okay, so now at this rate, we can kind of, split this into two different integrals. So here we have x minus 1 plus x. So here we have x plus 1 and here we have x divided by x plus 1. So this just remains as x plus we have the integral of, on this side we'll take x plus 1 divided by x into x plus 1 dx, right? And at this point we'll take minus we have the integral of x, here we are left with x, so x divided by x into x plus 1 dx. Now can't you see that you can easily cancel stuff over here? So we can cancel x plus 1, and we can cancel x and x. So we are just left with x plus the integral of 1 upon x minus we are left with the integral of 1 divided by x plus 1 dx. Okay, this is an easy integral now. So we are just left with x plus, we can rewrite this as the integral of x inverse minus we are left with the integral of x plus 1 inverse dx. Got it. So now what I'm going to do is, you know that very well, you cannot have a negative 1 ka power because then your rule doesn't apply. Then you're dividing by 0 because you have to add a power, divide by the new power. You can't divide by 0. So for that, we have our own identity. It is just x plus log of x minus we have the log of x plus 1. So at this point, we can just easily, kind of plus c obviously over here. So at this point, we can just use our logarithmic properties. So we have x plus, we have log of x divided by x plus 1 plus c. This would be your final answer. Okay, so we just solved a very beautiful integration problem over here. I feel like the key step was at this point where you have to add an x and minus an x, because that's where, you kind of solve it at the end. You need to look at the trick within these integration problems. You should see what they're asking. This looks like a problem that you have to simplify it. You have to first expand it and then simplify it. And we ultimately got our answer involving logs. That can also be possible. If you get a negative 1 power, always take a log. No question. Because you can never divide by 0. Always remember that. And never forget this constant of integration as well. So this would get you about 4-5 marks. Question, the integral of tan cube x divided by cos cube x dx. So now we just use our regular trigonometric properties. We have the integral of, instead of writing this as divided by cos cube x, we can take the reciprocal of it. We can say sec cube x. So we can say tan cube x sec cube x dx. Right? Now what I'm going to do is I'm going to break this tan cube x into two parts. I'm going to break it into tan square x and tan x. So I'll write this as tan x and I'll write this as tan square x. And I'll do the same thing with sec x. So I'll say sec square x and I'll break this into sec x, right? That's what I'm going to be doing in my next step. So I'll just say this is the integral of, now I'll take tan x into tan square x. But instead of writing tan square x, what I can say is I can say sec square x minus 1, because 1 plus tan square theta is equal to sec square theta. Okay? Sec square x minus 1 into, here again, I'll just write the regular thing, sec square x into sec x dx. Now I'll I'll put the sec square x and sec square x minus 1 together, and I'll put tan x and sec x together. Now I'm going to do some general substitution here, because if I take sec x the whole time, the problem will be very lengthy. In the end, we can change it back to sec x. So I'll take a variable here. Let sec x is equal to k. Let's just keep this as k, right? So let sec x be equal to k. So sec x ka derivative will be sec x tan x dx. So we can just say sec x tan x dx is equal to dk, because we've substituted sec x as k. So now that this is our thing, it will just be the integral of sec square x. So here we have kept sec x as k. So this we can say k square multiplied by sec square x minus 1. So we can say k square minus 1 dk, right? Dk, the integral of this. So we'll just say that the integral of, now this k square, we'll just have to multiply this. So k square becomes k to the power of 4 minus k square, right? Dk, k to the power of 5 divided by 5 minus you have k to the power of 3 divided by 3 plus c would be our integral. So k we substituted as sec x. So it will be sec to the power of 5x divided by 5 minus sec cube x divided by 3 plus c. This would be your constant of integration. So your answer is this. Okay, so from here, you just have to substitute sec x in terms of, you just have to write sec x as k, and so that you can take the whole derivative of it and make this dk. So this simplifies the problem. You don't have to solve each and everything. There's always shortcuts. So this is how we solve this. We have the integral of 2 divided by 1 plus cos 2x. Now what you need to remember is that the identity for cos 2x would just be equal to 2 cos square x minus 1, right? This is the identity for cos 2x. So if you put the value of cos 2x as this, we get the integral of 2 divided by 1 plus 2 cos square x minus 1. Now plus 1 will get cancelled with minus 1. We are just ultimately left with integral of 2 divided by 2 cos square x dx, right? So now 2 and 2 get cancelled. So we are just left with 1 divided by cos square x dx. So it's just the reciprocal of that. So it is integral of sec square x dx, right? And then you know that the integral of sec square x is just tan x. So tan x plus c. This would be our answer. Okay, so let's solve yet another tricky integration problem. So before I get into it, I want to actually teach you kind of an identity of formula that you guys need to remember. So you know that when we have x raised to n and we have the integral of that, it would just be x n plus 1 divided by n plus 1 plus c, right? Why are we doing this? We are doing this because x is a variable, right? But what if x was a constant? What if you have a constant here? It would just be the constant dx. But what if it's constant raised to the power of a variable x? In that case, you need to remember the integral of a to the power of x would just be equal to ax divided by log a to the base e. Okay, to the base e, any base you can take. So before we get into this integral, I just want to tell you that, because I don't want you to get confused, because we are going to be using this property in this integral. Now before we actually begin with this integral, let us first simplify it. So we have exponents here. So we have the integral of, first of all, we have 2 raised to x plus 1, right? So we can rewrite this as 2 to the power of x multiplied by 2, because 2 to the power of 1 is just 2, right? Minus we have now 5 to the power of x. We'll just write it as 5 to the power of x into, now we have 5 inverse. Now 10x, we can split it into two parts. Again, we have 2 and 5, so 2 into 5 is 10, so we can just write it as, this is 10 to the power of x, so we can say 2 to the power of x into 5 to the power of x. Split this integral into two parts, because obviously we can cancel things from both sides. So first I'm doing the integral of 2 raised to x into 2 divided by 2 raised to x into 5 raised to x minus of the integral of, now over here we have 5 raised to x into 5 raised to minus 1. So 5 raised to x into 5 raised to minus 1 divided by 2 to the power of x into 5 to the power of x. So 2 to the power of x into 5 to the power of x dx, right? Now from this integral, I can cut off 2 raised to x and 2 raised to x, and in this integral, I can cut off 5 raised to x and 5 raised to x. So ultimately, we are just left with the integral of 2 divided by 5x. So now over here, as I told you, whenever you have a constant within the integral, you can remove the constant out. So I'll remove 2 out here. 2 is a constant, so I'll remove it. So it'll just be 2 into the integral of 5x is in the denominator. So when it comes in the numerator, it will become 5 inverse of x dx. Because when I keep the constant out, when the constant is in the form of an inverse, I want to make it a fraction. But when it is within the integral, when it is a function, I want to make it in form of an inverse, right? So 5 inverse of x dx minus we have, now over here, again, I'll take the constant out. In this case, 5 inverse is the constant. As I told you, I want to leave it as a fraction when it's outside. So I'll say 1 by 5 into the integral of, now 2 raised to x is in the denominator. So when it comes in the numerator, it becomes 2 inverse of x dx, right? Looking good so far. So now what do I do? As I told you, I'll be using this identity. This integral of a raised to x is equal to ax divided by log a to the base e, right? So just like I said, I'll be using that identity. Now over here we have 5 raised to negative x. So I'll just be doing 2 into, we have, so 5 raised to x divided by log 5. But you have to be careful here. It is 5 raised to negative x, right? Since it's 5 raised to negative x, there's going to be an additional minus 1 over here. So basically this whole thing in the numerator is going to be, you know, in the form of a negative. This also we can keep as negative, right? I'm just saying, because when 5 is multiplied by negative 1, it just becomes negative anyways. I'm just writing this so you don't get confused, right? Now we have minus of 1 divided by 5 into, again, we have 2 2 raised to x. So when 2 is raised to x, it is divided by log 2. Divided to log 2 to the base e. We don't have to write to the base e, I'm just saying that for your reference. Now, since we've opened it up from an integral, we can add the constant of integration in this step itself. We can add the constant of integration. Now, just a little more simplifying is required. What you need to do is you can say everything in the numerator is in the form of negative, so this will be negative 2. Now, 5x will be 5 to the power of negative x, right? But I don't want that, so I'll take it down. So I'll say, I don't want any inverse, so I'll say 5x. 5 raised to x log 5, right? Log 5. This is the first part. Second part, what I can do is, I can just say, okay, I can bring the 2x down because 2x is 2 minus x anyways, right? Because it's on top here, because this is 2 minus x. Sorry, here it should have been 2 minus x. So if you get the 2 minus x below, it becomes 2x. So we can just say 1 divided by 2x and then into 5 log 2. So we can say into 5 log 2 plus c. And I think that's it. Yeah, this should ideally be our answer. Yeah, that's the correct answer. So negative 2 divided by 5x log 5 plus 1 divided by 2 raised to x into 5 log 2 plus c. This should be your answer. And this 5 log 2 becomes 2 raised to 5. You can write it. You can write that also. And you can say log 5 as log 5 to the power of 5x. But we don't really need to do that. That's not required. Okay. So now let us solve this one. It is the integral of x square plus 2 divided by x square plus 1. As I told you, I want to cancel off something between the numerator and denominator. So this we can say the integral of x square plus 1 plus 1, so you know is 2 divided by x square plus 1. Okay, now what we can do is we can kind of divide this into two different integrals because integration, right? Partial integration. So we can say x square plus 1 divided by x square plus 1 dx plus 1 integral of 1 divided by, we have x square plus 1 dx. So this gets cancelled, so it's just the integral of dx plus the integral of this, we can say dx divided by x square plus 1. This integral of dx, which is the x plus, now this is 1 divided by x square plus 1, which is this tan inverse x. That's something you need to remember. Tan inverse x plus c. This should be your integral. We have integral of 1 divided by 1 plus sine x dx. Now what I'm going to do here is I'm going to kind of rationalize it. I'm going to say 1 divided by 1 plus sine x into 1 minus sine x into 1 minus sine x dx. Why I'm doing that? Because see, I want to make this 1 plus sine x into 1 minus sine x because it becomes 1 minus sine square x. So I'll say 1 minus sine x divided by 1 minus sine square x. So now I can just divide it into two different integrals. So I can say that this is 1 divided by, now 1 minus sine square x, you know, is cos x, cos square x dx minus sine x divided by cos square x dx, right? So integral of 1 divided by cos square x becomes integral of sec square x dx minus sine x divided by cos x. Sine x divided by cos x into cos x becomes tan x. The extra cos x goes up, becomes sec x. So integral of tan x sec x dx. Now we just use our regular identities. Sec square x becomes tan x minus sec x plus c. This is your answer. This is a very easy integral. We have the integral of x cubed divided by x plus 1 dx. Now what I can do is I can add a 1 to the numerator, right? So then that will become the a cube plus b cube identity, and that splits into a plus b into a square plus b square minus ab. So then we have a plus b that cancels off with the denominator. So what I'm going to do is I'm just going to split this into the integral of, first of all, x cube plus 1. If I'm adding a plus 1, I have to also do a minus 1, right? Divided by, now what I'm going to do is this is x plus 1 dx. Now, since we have a minus 1, that becomes another integral. So we'll take the thing that cancels off together, a cube plus b cube divided by x plus 1 dx minus of the integral of 1 divided by, we have x plus 1 dx. Okay, so this is what this becomes. Now we can just rewrite this. We can split this. So a cube plus b cube identity, as I told you. So this becomes a plus b, a square minus ab plus b square plus 1, right? Divided by x plus 1 dx. Now, as you can see, x plus 1 gets cancelled with x plus 1. So we have to set the integral of x square minus x plus 1 dx minus of the integral of 1 divided by x. Now this we can just rewrite as x plus 1 inverse dx, right? So this just becomes x cube 3 minus x square divided by 2 plus x minus of, we have log x plus 1, right? We have log x plus 1 plus the constant of integration. That's it. I think, yeah, this would be our answer. Let's get to our last and final integration problem for this video. I always like to end off with something that looks difficult, but it really isn't. So we have this integration curve problem, and if you look over here, it looks like this will give you a hard time, but the solution for this is actually very easy. If you look over here, we have every single trigonometric ratio: tan, sine, cos, cosec, sec, cot. Now, what I'm going to tell you is, what if you just convert this cosec into 1 upon sine x, right? And you convert this sec into 1 upon cos x. And what if you convert this cot into 1 upon tan x, right? And now your entire problem is basically solved. When you convert this into 1 upon sin x, you take the LCM of 1 upon sin x and 1, and then you get an additional sin x over here, and then you get an additional cos x over here, and an additional tan x over here. Take the tan x, cos x, and sin x over here. Okay, so then you divide, you just obtain 1 plus tan x divided by 1 plus tan x, plus you have 1 plus cos x divided by 1 plus cos x, plus you have 1 plus sin x divided by 1 plus sin x, and then that just cuts. So you're just left with root of 1 plus 1 plus 1 dx, which is just the integral of 3 dx. Now you know that whenever you have a constant of integration, all you need to do is just the root 3x plus c. Or if you want to really write it like this, you can say 3 and a half, you can say, right, plus 1 divided by half plus 1. That also you can say plus c, right? Anything you want, and this you can simplify, or you can just write it like this. Okay, this would ultimately be your final answer. So this whole thing, you just have to simplify. You can simplify it just doing 3-4 steps, and then you get such a short solution, right? So that's pretty much it. You just need to apply that trick, and then your entire problem is solved. So now we have covered 2 integration videos. The first video was more of a basic introduction. Today I've dealt with some basic questions regarding indefinite integrals and how you can apply various identities. In my next video, we are going to be making a lot more progress on indefinite integrals. I'm going to teach you a few more properties, tricks, sums, plus I will be teaching you a very, very important concept in solving indefinite integrals, that is substitution. Okay, so I'm going to be teaching you this concept. Basically what, in short, when you have a function and you have the derivative of a function within the integral, you can take the function as t, or like I usually take it as k, and then you can take its derivative as dt or dk, and accordingly you solve it, and then in the end, after solving it, getting the integral, you replace t with the function you replaced it with. That is what we call substitution within indefinite integration, and that is definitely the most, important part of indefinite integration. Mostly questions come from there, where you have to substitute a function as something, and then you eventually take its derivative as dt, right? That is something that comes a lot. So I'll be teaching you the concept of substitution, as well as I'm going to be doing some sums related to the concept of substitution. I'll be doing various other concepts, plus I'll be covering some trigonometry as well, right? So we'll slowly make progress in this. I'll make sure you master indefinite integration. We'll keep solving sums, about 5 videos, I think, related to indefinite integration, and I'll make sure we together make progress in this concept, and then eventually we'll move on to definite integration. We'll go back, laugh at our mistakes, make progress, and that's how we learn, right? So we'll move on to definite integration right from scratch, and then again, just like indefinite integration, we'll cover many videos, right? We'll do many videos together, practice many sums, and then finally we'll be done with indefinite and definite integration. And before we know it, we'll be solving JEE level integration questions together, right? So it's all about patience and practice, and eventually you will become a master of it. And I'll also be, and after we are done with indefinite, definite, I'll definitely be doing a recap of differentiation with you guys, and then we'll be doing both integration, differentiation together, and then I'll be going into other aspects of calculus as well, and I'll also be covering some 10th grade math. I'll be covering quadratic equations, probabilities, statistics, as well as I'm going to be covering remainder factor theorem, basic algebra chapters very soon. Your 10th grade syllabus, basically, as you know, the batch right now is writing their boards. I'll make videos for the upcoming batches rather than the batch right now. So that's it for today's video. Thank you so much for watching, and I hope you learned something meaningful today, and I'll meet you guys in the next video.